dando prosseguimento ao nossa escola em teoria das foliações. Oh, I forgot, I have to speak in English. Today we are going to have the second class of Carolina Araujo on regular foliations on algebraic surfaces.
Okay, work. Okay, so good morning, everyone, and good afternoon for those in CIRM. So the idea of today's class is to work out a specific case of Brunella's classification of regular foliations on surfaces. So I remind you that yesterday we have reviewed the minimal model program for surfaces, and I stated the Enriquez-Kodaira classification of non-singular surfaces, minimal surfaces, and then I stated Brunella's classification of regular foliations on surfaces. So today I will try to explain the idea of the proof of the special case when the Kodaira dimension is negative. So let me state the result that we are going to prove today. So here, S will, as usual, denote a smooth non-singular surface, and F a regular foliation on S. But today we will assume that the Kodaira dimension of S is minus infinity. And then we have a classification in this case. Then, so there are three options. So the first case is then that the foliation F is induced by a, well, actually, maybe let me first say one more thing before I give the classification. Let me first say what S is. Then in this case, the first conclusion is that S itself is almost always a minimal surface. More precisely, S is the projectivization of a vector bundle E over a curve B. And F satisfies one of the following conditions. So the first case is when F is induced by this P1 bundle. So this is a P1 bundle. And the first case is that when F is induced by this vibration. The second case, F is everywhere transverse to this P1 bundle. And then in this case, we have two options. If the base B is rational, so if B is isomorphic to P1, then the existence of this transverse foliation will imply that, in fact, S is P1 cross P1, and F is induced by the other projection. Call it pi prime. And when the genus is larger, then in this case, this transversality will imply that we have that this foliation is can be recovered from the monodromy associated to. So this F comes from by the monodromy representation. Okay, so this is the transverse case, and there is one more case that happens in a very specific context, that F is a turbulent foliation with respect to an elliptic fibration that is transverse to pi. So what I want to do today is to give you an idea of the proof of this theorem. So let me recall some of the tools. So here are the tools, some of the tools that we are going to use. So in this context now, again, S, let me say just S is a surface, and F is a regular foliation on S. So the first tool that we discussed yesterday was the Baumbach formula. So I will refer to it as Baumbach. So it relates the Chern numbers of S with some invariance of the foliation F. So let me recall the two formulas that we saw. So there are many ways to state those. So let me write it as I did yesterday. So basically, the first formula says that the second Chern second Chern class of this vector bundle is 0, and this is just because the foliation is given by a non-zero section, nowhere vanishing section of this vector bundle. And if you write this down, you can let me write it this way. So this is the first Baumbach formula, and the second one says that the normal bundle of F squared is 0, and now using the relation between the normal, the tangent bundle of F and that of S, we can rewrite this. So this is just the C1 of S plus K of F squared. And this is C1 S squared. So the reason why I'm writing it this way, so there are many ways I can just write down combinations of these formulas. And one combination that yesterday we used, for instance, to show by writing a specific arrangements of these formulas to show that a K3 surface cannot contain a regular foliation. And today, if I think we take this one minus 2 times this one, then we get a formula that we are going to use today, which is this one here, that the C1S squared minus 2C2S is equal to KF squared. So this is the version of the Baumbach formula that we are going to use today. So another tool that I also want to mention is the Camacho-Sad formula. We'll abbreviate it in this way. And it says the following, that if I have a curve that is tangent to F, so under this assumption here, if C is invariant by F, then its square is 0. Okay, and then the third tool that I want to use is something that we have not discussed yet, which let me call it tangency formulas. So the idea is that we are going to use the canonical bundle and the normal bundle of the foliation to detect tangency between curves and this foliation or between two foliations. So let me start by recalling that we had this f can be described by this exact sequence. And so in particular, and then the claim, so first of all, let me take a curve in S that is generically not invariant by F, so generically transverse. So this is my curve C. Maybe I want to here. So here's my curve C. So generically, the foliation is transverse to C, but then there are some special points where we have tangency. And so we can define the tangency index between F and C, and this is a non-negative integer that counts with the appropriate multiplicities these tangency points. So we can define this invariant, and the claim is that this number, this integer, can be computed in terms of these line bundles. So the first formula says that this is just the normal bundle of F intersected with C minus 2 plus 2 times the genus or the arithmetic genus of the curve C. And it turns out that this is the same as computing the canonical of the foliation intersected with the curve plus C squared. So this equality here, well, it follows from two formulas. So first of all, the relation of the first Chern classes of this vector bundle. So the fact that we have that minus Ks is equal to minus Kf plus the normal bundle of F. And the usual adjunction formula that tells that for surfaces, that tells us that if you want to compute the arithmetic genus of a curve, you can do it by this way, Ks plus C intersected C. This is just the canonical bundle of C, the degree of the canonical bundle, which is 2 times PAC minus 2. So these two formulas give this two equality. So let me prove this claim. Okay, so we have seen already that a foliation F can be induced by a twisted one form. So this is the one form that defines, the twisted one form that defines F. And then we can restrict it to the curve C. And so this gives us a global section here. And this tangency index between the curve, the foliation and the curve, is nothing but the number of zeros of this twisted form. So this is the degree. So in other words, this is the degree of the divisors of zeros of this section. And this, well, this is just the canonical divisor on C. So the degree here is minus 2 plus 2 PAG plus the intersection of the normal bundle with C, which is exactly what we wanted to prove. Okay, so this is the first tangency formula that we are going to use. But there is another also very useful tangency formula which computes the tangency between two foliations. So we have our given foliation F. And now suppose that we have a second foliation on S. Then we can define the tangency divisor, let me call it D, the tangency divisor between F and G. So this is an effective divisor on S, and its support is precisely the union of the curves formed by the points where F and G coincide, where the two foliations are tangent. So this G, it may be a singular foliation, so this support will, of course, contain all the singular points of G. And then the second tangency formula tells us that this tangency divisor is linearly equivalent to NF plus KG, or in a similar way, NG plus KF. So I leave it to you as an exercise to prove this. And the idea is very simple. What you have to do is in order to describe this divisor, you can take a local one form defining F and a local vector field defining G. Then you contract them, then you get a function, and this divisor of tangency is just the divisors of zeros of this function. And then if you write this down, you just get exactly this formula. Okay, and then before we go to the proof of our theorem, let me just make a remark. That is going to be very useful. So suppose that we have a curve, a rational curve on C that has zero self-intersection. So whenever you have on a surface a P1 with zero self-intersection, then it induces, you can look at the linear system given by C, and then this will induce a rational fibration on S. So then the linear system will induce a fibration to some base B, and this fibration, and this C is a fiber of pi. Sorry?
We might need a multiple of C.
No, in this case, in the end, I think C should work.
B has a genus.
Any genus. Okay, maybe, let me say that C induces, then get, maybe one have to take a, you're right, maybe one have to take a multiple of C, I'm not sure. So we get this, in any case, we get a fibration whose general fiber is a rational curve. So that the inverse image of a point is this C. Okay, so it may have some singular fibers, but the general fiber is P1. Now, if this curve is tangent, is invariant by F, then, of course, the normal bundle of F intersect C is going to be 0. And then this will be true for every fiber. And therefore, from the tangency formula, it will follow that F is induced by this rational fibration. Indeed, if F were not induced by this rational fibration, then I would take a general fiber would be not invariant by it, but then by using the tangency formula, you would get a negative number for the tangency between F and C, and this is impossible. So in fact, it has to be, F must be induced by this fibration, and then because it is a regular foliation, it is in fact a P1 bundle. Okay, so now I think these are the tools that come from the assumption that that S admits a regular foliation, and we will also make use of the theory of algebraic surfaces, Riemann-Roch, junction formula, the intersection form, etc. And now I think we can proceed with the proof of the main theorem of today. Okay, so let me recall that yesterday we discussed the minimal model program for surfaces. So what we saw is that if you are given a surface S, after you can look for -1 curves. Whenever you find a -1 curve, you contract it, and then after a finite sequence of blowdowns, you get to a minimal surface. And in this case, because we are assuming that the Kodaira dimension of S is negative, this minimal model has to be a ruled surface, either P2 or a ruled surface. We don't have to worry. We know that S is not isomorphic to P2 because we have already proved that P2 does not carry any regular foliation. So in the end, what we do is we start with our surface S, and then we contract some -1 curve, and then we do it finitely many times until we actually get to a ruled surface. We call this B over some curve B. So the general, so what we get, we may have some reducible fibers, but the general fiber is a P1. So this is what the minimal model does to the surface. So this last surface here is the projectivization of a vector bundle over a curve B. And so the idea of the proof, let me call this composition here, pi. So the philosophy of the proof is to compare our foliation F with the foliation induced by pi. We call it G. And by comparing, well, we have this, for instance, the tangency. We have this three tools that I explained that we are going to use to make this comparison. And now we will divide the proof into 2 steps. So in the first step, we will in fact prove that there are no blowdowns to be made, in the sense that in this first step, we will prove that S itself is a ruled surface, is the projectivization of a vector bundle. And then we are going to be in this simpler situation, and then in this simpler situation, we are going to classify the regular foliations. Okay, so in order to, so the first, maybe first step, we will prove that S itself is the projectivization of a vector bundle over B. Okay, and to do that, we are going to use the Baumbach formula. And remember that the way I stated it today, it involved the first and second Chern classes of the surface. So the first thing that we are going to do is let's compute the first and second Chern class of this minimal model S prime. And then let's compare with the ones of S. So, okay, so let's compute. So if you compute the first Chern class squared of a ruled surface, well, there is a very well-known formula. This is just 1 minus the genus of the base. 8 times 1 minus the genus of the base. And now this for the second Chern class, well, this is the topological, coincides with the topological Euler characteristic of S prime. And because this is a P1 bundle over B, this is just the product of the Euler characteristic of P1 and that of B. And then this can be computed. So this is 2 times 2 minus the genus of B. And so this is, if you compare here, what you have is that the C1 of S prime squared is 2 times the C2 of S prime. So this holds here in the last step for the minimal model. Now, we will check what happens at every step that we blow up a point. So it's very easy to see what happens. So if S tilde is the blow up of a surface S, let me write it for S prime, then their Chern classes are related as follows. So this is an easy computation on the surface. So this is just the C1 squared minus 1. So every time that I blow up a point, the square of the first Chern class drops by 1. On the other hand, Now, if you see what happens with the second Chern class, then what we are doing here is we are replacing a point by a sphere. And so if you use the interpretation as the Euler characteristic, then you check that this is the second Chern class of S plus 1. So the C1 square always drops, and strictly drops, and the second Chern class strictly increases. So the conclusion that we have is that for our surface S, we have that C1 square is less or equal than the C2 of S. And we have
You are talking, Carolina,
Yes?
you are talking about S prime, no?
No, now I'm talking now. So on S prime, we computed, and they are equal. On these two classes are equal. Here, sorry, this is. And then we checked that every time that we blow up a point, this one decreases and this one increases every time that we blow up a point. So after finitely many blow-ups, what we get is that they were equal in the first step. This one decreases, this one increases, so we have this inequality. Is that okay? It's okay, Frank?
Yes, but just the line over, the top line.
No, here,
S prime.
Sorry, yes, thank you very much, yes.
Okay, thank you.
Thank you. Okay, so we have this inequality, but in fact, if we have more, we have equality here if and only if, in fact, S is the projectivization of S is equal to S prime. And so in order to show that S is in fact minimal, what we have to show is equality. And so the goal then is the following. So the strategy is that the strategy is to show that the converse holds, so C1 squared minus 2C2 S is greater or equal than 0. So if we prove this inequality, we will then conclude that we have equality here. And thus S is isomorphic to the projectivization, is a ruled surface. So this is the idea. But now, and this is where the foliation plays a role, the Baumbach formula that I reviewed today says exactly that this number here is equal to kf squared. So this was the version of the Baumbach formula that I stated. And so this is what we actually have to prove. Okay, so need to prove that kf squared is greater or equal than 0. And we are going to divide it into two cases.
So at this point, you are assuming that F is not a rational vibration, right?
Okay, yes, we can assume from the beginning that, sorry, I did not write this, but we can assume from the beginning that F is not induced by this rational vibration, otherwise we are done. Okay, so now we have to to prove the positivity of that self-intersection. So let me do the first case. I will divide it in two cases. So the first case is that, so we suppose that the canonical bundle of the foliation is effective, so that we have sections here. So this holds, for instance, whenever the curve has positive genus. So if the curve G, for instance, has positive genus, then we can find a global one form on the base, and then we can pull back to S, and this is going to give us a one form on S that that will induce a global section here. So whenever the base has positive genus, we get such section, and so we can take then a divisor D. So we have an effective divisor D. Let me write it effectively as sum of AI DI. So this is an effective divisor that is linearly equivalent to F. And in order to show that the K has positive square, it is enough to show that it has non-negative intersection with all the DIs. Now, if the DI itself has non-negative positive intersection, then of course this holds. This is an effective divisor. So this case is okay. And now let's see what happens when I have one component of this divisor that has negative self-intersection. So if the DI has negative self-intersection, okay, so the first observation is that it cannot be invariant by F. So this is given by the Camacho-Sad formula. DI is not invariant by F. And so we can compute its tangency index, which is a non-negative integer between F and DI. And if you use the tangency formulas, what we get is that this is the canonical times DI plus DI squared. Now, this is by assumption negative, but this index is non-negative, so this implies that Kf dot di is greater or equal than 0. In fact, even greater than 0. And then with that, we can conclude this, this case. So this finishes the first case, and we are able to prove what we wanted, which is that the K has positive, non-negative square. Okay, now the second case is when we do not have sections in this, or this bundle. So that is, this is not an effective divisor. And in this case, as we have seen, the base has to be P1. And therefore, S is in fact a rational surface. Okay, so in this case, we could not pull back, we could not get a section here, because of course we could not pull back a one form on P1, but we can pull back a one form with 2 poles. And this gives us a section here, not of the canonical of F, but the canonical of F plus 2 times F. So here F will always denote a general fiber of the fibration. And this has to be, this is now in fact effective, so we can find a global section there. And so this is what we have, and our goal is to show that in this case, when we do not have KF effective, the normal bundle instead must be effective. So we want to prove that the H naught of NF is effective. And okay, what we will do is to show that this is effective, we will use the Riemann-Roch theorem that computes the Euler characteristics. So in order for the Riemann-Roch to give us a good lower bound, we have to control the H2 of this normal bundle, and this is just, so this H2, or in other words, by Serre duality, this is the H naught of Ks minus NF. So this is, we want to show that this is 0. So this is claim. I want to show this. And once we show this, we have the Riemann-Roch formula that will give us a lower bound for this H naught, and this lower bound will in fact be positive using the Baumbach formula. So to show this, let's assume otherwise. So if this is non-zero, this is non-zero, then we have a section here. We had a section of Ks plus 2F. And here we use this section to produce a section of Ks plus, sorry, K. Here is Ks minus an F plus Kf plus 2F. So we get a section here. But now this one here, this is just NF plus Kf. This is just Ks. So this is 2Ks plus 2F. But on the other hand, and so what we are getting is a divisor, effective divisor. This will yield an effective divisor D that is linear equivalent to Ks, 2Ks plus F. But now the adjunction formula, on the other hand, tells us that Ks plus F. So this divisor D, of course, it intersects F non-negatively because F is a fiber, and this is an effective divisor. And now, but on the other hand, if I intersect this with F, the adjunction formula tells us this is exactly minus 2. Minus 2 minus the 2, the genus here of the F is 0. But on the other hand, this is just D over 2 times F. And so this is a contradiction. And so indeed, we conclude that this line bundle has no sections, And so, as I said, we can now use the Riemann-Roch to estimate this H naught. So Riemann-Roch will imply that the H naught of S and F is positive. Okay, when I say Riemann-Roch, well, we have to write down the formula and again make use of the Baumbach formula to rewrite the right-hand side in terms of the second term class, which we can control. Okay, so the NF has sections. Let me try to speed up a little bit. So the NF has sections. So that means that we can find. Actually, we can even, when you write down the Riemann-Roch, you can actually get this very, I think this is greater or equal than 3, I believe. In any case, it is positive. What I'm trying, I just want to say that this divisor here, an effective divisor representing an F is non-trivial. So we have that this F is linearly equivalent to, in fact, an effective divisor. And so, again, we do the same trick. We write this as a sum, a positive sum of divisors. And then, again, using the Baumbach formula, Camacho, Sade, and the junction formulas, all the theory of surface, we actually show that each di is, in fact, a rational curve. So this can be detected by the junction formula with the intersection of K and the self-intersection. So the idea is more or less the same as we used before. Okay, so if the di's are not invariant, then we can, so let me just write this. If this di's is not invariant by F, then we can use the tangency formula to compute the tangency index. And this will give us that NF dot bi is greater than 0. But on the other hand, by Baumbach, we know that NF square must be 0 for a regular foliation. So the conclusion is that this normal bundle can be written as a sum of effective divisor, and all of these components that appear in the support are in fact invariant by F. So we conclude that in fact the I is invariant by F. Well, it is isomorphic to P1, and its self-intersection must be 0. In other words, what this is saying is that in this case, the F is induced by this P1 bundle fibration. And so we are okay. So this F, in this case, this F is induced by the P1 bundle. So in fact, this vibration might be our given vibration, or it is transverse to it, which is exactly the case where S is P1 cross P1. So we conclude that F is induced by a vibration, rational vibration, with fiber di. And I think my time is over, and I have not said anything about the second step. So let me just briefly give you an idea of the second step. So this finishes the first step. So we have proved that, in fact, our S is a P1 bundle over a base B. And moreover, in the case when the base is P1, we have pretty much made the conclusion. So let's assume that, so we already know this, that S is the projectivization of a vector bundle. And let's assume that the genus is at least 1. Then what we do is to consider the divisor of tangencies between our foliation F and the foliation G that is induced by this vibration pi. So we write down this divisor. We know that this is linearly equivalent to Kf plus Ng. We can compute the Ng in this case because the Ng is just the pullback of the tangent bundle of B. So in this case, so this Nd here Ng is just the pullback of B, which is numerically equivalent to 2 minus 2GB times F. In other words, if we write this down, we get that the Kf is linearly equivalent to D minus Ng. And remember that in this case, we had already concluded in the first step that Kx squared has to be 0. But then if you rewrite it using this formula, what you get is this number here, D squared plus 4 times GB minus 1 times dF. So let me just not write this down, but let me just say it loud how the proof goes. So if you write down, so if you look at this, formula, the only way that it can be 0 is that, so actually one can actually show that this D squared is always greater or equal than 0. This is using the same tricks. You write it as a sum of effective cycles, and then you restrict to each component, and then you work it out. And then once you have this, the only way that this vanishes is that either if the genus is 1 and the D squared is 0, or if the D dot F is 0. So when the D dot F is 0, this is telling us exactly that the foliation is everywhere transverse to G. And then the other case, well, requires when the genus is 1, then it requires a little bit more work to construct the elliptic fibration that is transverse to the P1 bundle, and then because d square is 0, you get that this is going to be a turbulent foliation. So let me stop here, and thank you for your attention.
Are there any questions? Frank, do you have any question from your side?
Question? We have a question.
Thank you. I want to know what happens if in the proof your G is also a regular foliation.
If also what, sorry?
G, the order foliation different from F.
Yes, so it could happen exactly in this case that, so in this case, the first thing that you prove is that so here, this D's, notice that this tangency, if this divisor D contains as a component a vertical fiber, then G coincides with F. So we can assume that our D is in fact transverse, and if D is 0, this means that the foliation is transverse to pi. And then if actually D is completely 0, they're everywhere transverse, then this is just a suspension of the monodromy. This is given by the monodromy representation. And there is the case when the D is in fact non-zero, and then in this case you show that the genus is 1, and then you construct a fibration in the other direction, which will be the elliptic fibration with respect to which the F is turbulent. But then, okay, this does require a little bit of work. I have not really discussed this part.
And so this case really happened, the case of turbulent foliation.
Yes, it could happen. For instance,
so we have example.
The S could be a product.
Mm-hmm. Okay.
Thank you. So fast to take the base elliptic curve times P1 and a rational one form on P1 plus a form on the elliptic curve. So
exactly,
this gives
yes.
turbulent.
Yes, okay. Thank you.
Any other question or comments? Okay, if not, let's thank Carolina again.